Good afternoon, everyone. It's my honor to introduce Professor Kazuyuki Tanaka. He was my supervisor when I was a graduate student at Tohoku University, and now in BIMSA, he's still my supervisor. Today, he will give a talk on reverse mathematical reconsideration of lower Borel games. Welcome. Please start.
Thank you very much for your kind introduction, and thanks to the organizer for giving me this opportunity to talk about my research. So I mainly, can you hear me? The mic is okay. Reverse mathematics is a foundational program which began in the 1970s to answer a pivotal question: what set existence axioms are needed to prove theorems of ordinary mathematics. Reverse mathematics is deeply connected to Hilbert's program proposed in the 1920s, and it's sometimes referred to as its modern realization. The Hilberts aspire to rebuild all of the mathematics as a consistent formal system, but the work of Gödel, Church, Turing shows that this goal was ultimately unachievable. Then abandon the complete formalization of all mathematics. Harvey Friedman and Steve Simpson, maybe others, introduced several hierarchic subsystems of second-order arithmetic as necessary, and thereby expanding and complementing our understanding of the logical foundations of mathematics. I have been working on reverse mathematics for many years, and more recently, my research has focused on the collapse phenomena in the hierarchies that emerge in reverse mathematics. For instance, hierarchy reduction by restricting a class of formulas that is conservative extension. That technical term was explained in Professor Chon's lecture a few days ago, and or by restricting a class of target structures, just restricting a class of structure or formulas, we collapse some hierarchies. And others, I have been investigating the determinacy of Borel games at lower complexity levels, such as sigma 02, which is also called F sigma set. F sigma is a countable union of closed sets, and which still needs stronger action. That means stronger than the usual axiom of reverse mathematics. Needs a stronger axiom based on the notion of inductive operators and fixed points. These notions are very useful to define very high-level sets. Okay. On the other hand, mu calculus is a framework used by analyzing property of transition systems by way of least and great fixed points operators, mu and nu. It is also known that the hierarchy of mu calculus corresponds to the determinacy hierarchy over different classes of sigma 02 games. So I'm interested in the collapse phenomena in the hierarchy of mu calculus too. In today's talk, I provide a broad overview of my research domain. Also, the core aspects of my study are too technical to detail fully in this setting. I hope to convey the general concepts clearly enough that you will leave with a good understanding of the key ideas. Okay. So here are contents. So some topics are very elementary. I start with first order logic, and then extended to model mu calculus, and we discuss determinacy strengths somewhere here. And also I explain reverse mathematics. Okay. Now, part one, first order logic and the enshrinings problem. David Hilbert attempted to solve difficult problems like the continuum hypothesis by reducing them to the enshrinings problem. The English translation is the decision problem. The enshrinings problem of first order logic, that is a framework in which most mathematical theories are formulated. In particular, set theory are formalized in first order logic. What is first order logic? First order logic only treats the following two types of quantifiers. Universal quantifier means for any elements x in the object structure, just x ranges over the object structures. And existential quantifier means there exists an element x of the object structure. Okay. Just restricted to the range of variable. And besides usual propositional connectives and mathematical symbols, you need there. Then Hilbert, with his student Ackermann, wrote in their book Grundsicher, their theoretician logic, that they wrote, enshrining problem is solved when we know a procedure that allows for any given logical expression to decide by finite many operations its validity or satisfiability. So enshrining's problem is solved when you find an algorithm to decide validity or satisfiability. Then enshrining's problem must be considered the main problem of mathematical logic. Yeah, they wrote so in this book. Then after that, many logicians attempted this problem. First, first order theory of natural numbers with only addition. That theory is decidable. Okay. So given formula is true or false is decidable. For this theory, that is proved by Pressburger. Okay. Just remember, that book is appeared in 1928. Then soon Pressburger showed this theory is decidable. And the Skolem proved that the first order theory of natural number with multiplication is decidable. Almost the same time, Frank Ramsey, in his famous paper on the problem of formal logic, appeared in 1930, introduced a theorem now called Ramsey theorem about partition to deal with a simple case of enshrining's problem. So Ramsey invented some combinatorial theorem to solve enshrining's problem, but only special case. On the other hand, there are undecidable result. Gale proves that any first or higher order theory, including arithmetic, now he must include arithmetic, has an undecidable proposition. So in particular, first order theory of natural numbers with addition and multiplication is undecidable. Okay. Just plus or times are decidable, but if it has both, then theory is undecidable. The paper has this title, über Homer and entscheidbar, that's their Principia Mathematica und something. And anyway, this paper is also about undecidability. This paper is famous about incompleteness theorem, but actually, Goethe didn't prove incompleteness theorem. He proves undecidability theorem. Okay. And then Church and Turing independently proved that validity or satisfiability of first order logic is not decidable. And Turing's paper, that is also very famous because he defined the Turing machine in that paper. And the title of the paper is on computable numbers with an application to the Entscheidungs problem. This is written in English, of course, but here I use German word. So this Entscheidungs problem is very important. Many people try this problem in this area, in this era. Then finally, they show this problem is not solvable. But even though there are still some decidability result, Tarski proves that the first order theory of real closed field is decidable. Also, the decidability of real exponential field is still unknown. So this is a field with exponential operation. That is unknown. Then also many people try to extend the decidability result of first order logic to more general logic, particularly second order logic. First order logic, FO, is many good points, particularly almost all mathematical theories can be formulated in first order logic. Yeah, I mentioned that like PA or ZFC are first order theory. But many simple properties of structure cannot be described by first order formula. For instance, the domain, finite domain or finite structure has an even number of elements, or given structure, a given, consider structure as a graph. Then graph is connected or not. Just this property is the second order property, and you cannot express it by first order formula. Now, monadic second order logic, MSO, is the first order logic plus quantifier range over subsets of structure for all x, capital X ranges over domain of the structure, and the subset X of the domain. Or similarly, we may use a unary predicate for all predicate Px, or exist predicate Px. Okay, this unary predicate can be thought as just a subset. Then second order logic, general second order logic is not unary, just any n-ary predicate or n-ary relation can be used for quantifier. So also you may use a function quantifiers. If you can use a pairing function, then second order logic and the monadic second order logic are the same. You're using a pairing function, you can express this as just a unary predicate. But we are thinking about mainly theory without pairing function. So the parity of a set, oddness or evenness, or parity of a set can be defined by using a function. So it's more, they have a more expressive power than first order logic. Still, some theory are decidable. First, monadic second order theory of natural number with just successor operation. It's called S1. S is decidable. Okay, this is proved by Bucchi. And to show the decidability of S1, S, Bucchi define omega automata that accept the infinite world if during the reading the input, finite state appear infinite many times. So this is the image of a usual finite automaton. Finite automaton read a finite sequence of symbols. Then starting with initial state and then read all symbols if machine is in final state, then machine accept this sequence. But omega automaton read infinite tapes. Then it accepts certain final state appear infinite many times. Okay. Then emptiness problem, or emptiness means the language of sequence accepted by automaton is empty or not. Or universality problem, the language, accepting language is the whole set or not. That is decidable. Okay. Even certain infinite automata, like omega automata, that these problems are decidable, then theory expressed by such an automaton are decidable. Okay. Then Rabin extended Bucchi's argument to tree automata. Then he proved that monadic second order theory of binary sequence, this is a set of finite sequence from 0 and 1 with the two operators. There are two types of successor function, adding 0 or adding 1. Then this theory called S2S is decidable. His original proof was very complicated, and there are many improvement or just simplify some part with help of something. And particularly, Grevich-Harrington simplified the Rabin's proof by using infinite games Another simplified proof uses a model mu calculus. These concepts are deeply related to each other. Now, from end-siding problem to model checking. End-siding problem is a fix object structure or theory. You fix it, then input formula or proposition phi, then decide whether or not phi holds in M or theory T. Okay, this is input. Phi is input, and decide it holds or not. That is a decision problem. But model checking is also, the model is input. Input the model that the finite transition graph M and the formula phi, and decide whether or not phi holds in M. So state transition graph is just how to say that? Usually that is a finite graph, but it's possible to have infinite graph. Then phi is a specification. It's some property. For instance, system includes some kind of errors or some kind of infinite loop, or such a property is expressed by formula. Then decide the model satisfies phi, or phi satisfy or not in M. That is a model checking problem. This is quite important and really used system, and particularly SMV, symbolic model verifier, is a widely used model checking tool developed at Carnegie Mellon University that analyze finite state systems by using temporal logic, CTL, and CTL standing for computation tree logic. This logic is propositional logic with many operators. Actually, not usual model logic, but use operator X for next, and F eventually pass quantifier A. That means for all pass and others. This is very complicated logic, but a small part of CTL is a modal logic. The modal logic is a proposition logic plus some modal operators, simple modal operators like the box and diamond. And CTL and its variation can be straightforwardly translated into modal mu calculus. So mathematically, this is simple and very powerful. But actually, this is too strong to decide true or false. Then modal logic is a subset of first order. Okay, this is embedded into first order. Modal logic is propositional logic with modal operators, and usually use box and diamond. Box is something like a generalization quantifier, and express for all next step something false. And diamond is an existential quantifier, some next step p holds. For instance, so there's just this part of the system, P holes at these states, then box P holes here, because all next step P holes. So at this node, box P holes. And diamond Q holes here, because Q hole here, also these are negation of Q. So more formally, on a transition system, it's a graph, directed graph. V is a node, and E is the edges. And model formula, phi, is translated in the first order formula, ST, S phi. ST is for standard translation. So phi falls at S, translated in the first order logic is like this. Box phi holes means for all T, there's an edge from S to T. For such T, phi holes. So this is a translation of box phi. And similarly, translation of diamond phi is there is a next node such that ST phi holes. So modal logic is just a weak version of first order logic. But what is a modal mu calculus? Modal mu calculus is obtained by adding mu and nu to modal logic. The standard translation of modal mu calculus is obtained by standard translation. Mu x dot phi holes at S means all x. This capital X may be included in phi. Okay? And for all x, for all t, phi holes at t, then t includes x, then S included in x. So roughly it says x is a smallest set of T such that P holes. Instead, mu x is a largest set such that P holes. And I give you example. First, mu x dot P and box X express always P holes. Since standard translation is there is a X including S and P holes at all T X, and the X is closer on the next step. Yeah, if you compare it with this definition, yeah, it's not difficult. But this express always P holes. Then its negation is also given as this, and this is rewritten as this, and finally this. Yeah, this is a essentially De Morgan rule, but some places must be careful because also two negation appeared in this transformation. Then this formula express eventually not p-holes. Then this formula somewhat it's takes time to be familiar with this kind of expression, but this express as there exists a path where p holds infinite many times. Okay, then question: does expressive power always increase with the number of fixed points? Excuse me, I need water. About alternation hierarchy mu n pi mu n sigma mu n pi mu n, the classify formulas of mu calculus by the alternation depth, that is number of alternating blocks of greatest and least fixed point operators. So in this case, just alternate mu and nu, and so the complex is 2. And starting with nu, so that is pi mu 2 formula. Then I'm interested in the strictness and collapse of alternating hierarchies. First, if we consider the condition or certain restrict class of transition system. Yeah. No restriction, then the hierarchy is strict. So sigma nu n and pi, these are defined different sets. But if you adding conditions on transition system, like if just thinking about transitive relation, then hierarchy, alternating hierarchy collapse to alternation-free fragment of mu calculus. Alternating free means no nested alternation. This is a nested alternation, but only, of course, there's only one operator, then this is not nested. But even two variables used, but if there's no nesting or no tanglement, then it is called AFMC. So the all formulas are equivalent to formula in AFMC. You don't need the nested quantifier to express any hierarchy, any class. So yes, putting some relation on conditions on transition system, we check the hierarchy is collapse to some levels or not. Then Yeah, these conditions in blacks are already known, but blues are the new one. Mainly, this is a result proved by Leonardo Pacheco, who was my student in Tohoku. And then, yeah, we characterize these collapsing phenomena. But probably important is the strictness of these. This is proved by Bradfield some time ago, and he used mu arithmetic developed by Lubarsky, and mu arithmetic is a monadic second order arithmetic with mu nu instead of existential quantifier. And Bradfield deduced the strictness of modal mu calculus from the mu arithmetic. And this is some idea about the definition. Phi is a pi arithmetical mu n formula, then mu x dot phi is sigma arithmetical n plus 1 formula. Just because of this, it's sigma n, sorry, this is a set, expressing set. And some term belongs to this. This is set term. T belongs to this set term is a formula, and this is called sigma a mu n plus 1 formula. Yeah. Just the idea of the class of formula. Then the set of even number is defined like this: mu x dot something. Yeah, this means that x is equal to the set of small x such that satisfy this. So x appears both sides, and take smallest such x. So x is a set of small x satisfying in this, and take, yeah, for instance, if x is the set of all numbers, then yeah, x equal to this, but consider the smallest such x that is expressed mu x dot something. And this is denoted by mu x dot something, and this is sigma 1 arithmetical mu formula. Similarly, the set of odd numbers is also expressed mu x dot x equals 0 or this formula. Okay, then take complement. Taking complement of this, you get this formula, and this is pi 1 formula. So this formula is expressed by sigma 1, and this is pi 1. So this is also delta 1. Yeah, in that way, arithmetical, in mu arithmetical, there's a certain hierarchy built. Then the Bradfield established the relation between mu formula and mu arithmetical formula. Let M be a recursively presented transition system. Okay. Some way it is expressed by some computable method by natural numbers. Then by Pm, we denote the set of integers at which phi falls. Okay. This phi is I mean, mu calculus. It's not mu arithmetic. Then, because this is treating a transition system, then Bradfield showed that for any sigma mu n formula, phi, then the set of states phi holds is sigma n a definable, sigma defined by sigma a formula, and conversely, for sigma a n formula psi, there is a m and sigma mu n formula such that psi and this model is equivalent. Okay, then, wow. Just here we explain the reverse mathematics briefly. And so 1920s, Hilbert formulated the system Z2, in which most of mathematics can be developed. Then 1970, Friedman began to study which subsystem of Z2 are necessary and sufficient to prove theorem of ordinary mathematics. In 1980s, Simpson systematized the study as a reverse mathematics. So the main question is which axiom, particularly set existence axioms, are needed to prove theorem. First, fix a base theory, T, and pick a theorem of ordinary mathematics. To find the weakest axiom alpha to prove tau. So T plus alpha proves tau. Then very often we can show T proves alpha and tau are equivalent. Okay, this is a reverse mathematics phenomena. To define, to develop reverse mathematics, we need to introduce the classification of formulas. Yeah. So this is maybe to anyway. Yeah, I will explain. Arithmetical formula sigma 0n or pi 0n, and also it is denoted by sigma 1 0. And sigma 0 n formula is n blocks of quantifiers, alternating quantifiers, starting with existential quantifier. And pi 0 n is starting with generalization quantifier. And the inside is a bounded formula like this. And analytical formula is classified as sigma 1n and pi 1n. And sigma 1n formula start with existence sets x1. This is a sequence of sets. And pi 1n is for all sequence of sets x1. Yeah, this is just a finite sequence. Why? Because we have usually pairing function, so we have just one set quantifier is enough. Just alternating one existential quantifier, generalization quantifier, etc. And the delta 1n is sigma 1n and also pi 1n. And these formula express a set of natural numbers on a set of reals or set of functions in. This is a sequence of natural numbers, okay? This or Borel space. Express a subset of n or express subset of n to the n. Then x is SE, computably enumerable. It is expressed by sigma 01 formula. And x is computable. It is expressed by delta 01 formula. And using this, also we can classify the set in bare space. G or open sets. Open sets are expressed by sigma 01 formula. And G data set is a pi 02 formula with actually parameters. And A is an analytic set, that is sigma 11, and etc. These are called Addison-Green hierarchy. Using this classification, yeah, there are five subsystems of Z2 are defined. Usually our base theory is RCA node, that is delta 01 comprehension, that is delta 01 means computable set. So it roughly said the computable set exists. And sigma 01 induction is induction on computably enumerable set. Okay. So anyway, RCA 0 is kind formalization of computable mathematics. Then WKL node is RCA node plus any infinite binary tree has a infinite path. This is called a weak Koenig's lemma. So even if infinite binary tree is computable, it may not have any. It may not have a computable infinite path. Infinite computable path. Infinite binary tree has an infinite path. This is the true. This is a fact, but restricting to computable world, infinite binary computable tree may not have infinite computable path. So assuming infinite computable tree has an infinite path is asserting something non-computable. Okay, so this is stronger than RCA. And ACA is RCA 0 plus arithmetical set exists. Or it's possible to say sigma 01 set exists. Sigma 01 set exists, then using oracle or parameter, if sigma 01 set exists, using that as an oracle, you can show sigma 02 set exists. And using that oracle, you can prove sigma 03 set exists. So arithmetical comprehension is the same as sigma 01 comprehension. And ATL node is a RCA node plus arithmetical transfinite recursion, existence of transfinite hierarchy produced by iterating arithmetical comprehension. And pi 11 CA is RCA node plus pi 11 comprehension. Then some popular result of reverse math is RCA node proves intermediate value theorem or fundamental theorem of algebra, and WKL node proves maximal, etc. Then one of the important meta theorem of reverse mathematics is the Friedman's conservation result. WKL node proves sigma. Sigma is a pi 02 sentence. Then that sigma is already provable in PRA. PRA is a primitive recursive arithmetic, just consists of the definition of primitive recursive functions. That's all. Then, so WKL0 and PRA has the same consistency strength. So this is a very clear system, but it's also use these theorems are provable, so it's very rich theory, rich mathematical theory, but it is yeah, surely consistent system. Then, yeah, Harrington, he's my supervisor actually, and Harrington proved that the WKL0 is conservative extension of RCA node with respect to pi11 sentences. Then I, with Simpson and Yamazaki, extended this result to this formula. For all x, there is a unique y such that p is arithmetical. So for this conservation, there's nothing claim existence. But here, this is a existence claimed in the statement. So for instance, fundamental theorem of algebra, there is a polynomial, there is a unique factorization. Okay, the polynomial has a unique factorization. That is this type of statement. Then if it is provable in WKL node, it is already provable in RCA node. This is very useful result. So this is also a hierarchy collapse, hierarchy of reverse mass systems are collapsed for this formula. And more, yeah, some generalization of this theorem are proved. Yeah, skip this. This is the picture of reverse mathematics. And at the beginning, many mathematical theorems are found on orbit of the major planet, like so open determinacy. Yeah, we haven't expressed that. This is on the orbit of ATR node. And the convergence of Cauchy sequence is here. And also some Heiner-Borel theorem is on this orbit. But recently, there are many theorems are found, particularly between ACA node and WKL node. Yeah, there are many theorems are explained in the Professor Chon's talk. Okay, then we are thinking about games now. So Professor, you defined the Gale-Stewart game already, so we just quickly look at the players just to choose numbers, and the sequence belongs to a given set, then player one wins. Then set X is determined if player either player one or two has a winning strategy. And originally, Gale-Stewart proved open games are determined. And later, Martin proves Borel sets are determined, while analytic sets are, some analytic sets are not determined. Also, to treat the complement of omega tree language, Gurevich-Harrington introduced a forgetful game. But recently, this is more elegantly reformulated as a parity game or memoryless game with parity. And so the decidability of S2S and the determinacy of omega tree language and the decidability of modal eucalculus and determinacy of parity games, these deeply related to each other, and essentially is the same, same functions. So determinacy strengths reduce when it is restricted to the space. So we originally think in bare space, and bare space open games are determined. That is equivalent to ATR node. But instead of bare space, if we consider the Cantor space, the space of sequence of zeros and ones, then open determinacy is equivalent to WKL node. And so like a pi 02 determinacy, for instance, is equivalent to pi 11 TR for bare space, but restricted to the Cantor space, this is equivalent to ATR node. So as these strengths are reduced. Also, furthermore, we just this is the Cantor space, but furthermore, we restricted to the definition of delta 01. Delta 01 is including any oracle, but if we consider the certain set defined by machine, then any omega regular game, so the game defined by omega automata, that is boolean sigma 02 set, that is effectively determined with a computable winning strategy. So in fact, this is provable in RCA node. This is a determinacy about B sigma 02, but it is provable in RCA node. And this is omega automaton, but extended omega deterministic context-free language. It is still computable. Determinacy is still provable in RCA node. But this is deterministic context-free. Deterministic. The next step is unique. Non-deterministic context-free is the situation is greatly changed. Omega context-free. Actually, omega context-free is sigma 11 set. Omega context-free determinacy is equivalent to sigma 11 determinacy. That is also proved. Even restricted to Boolean sigma 02, this cannot be proved in RCA node. But our recent work with mainly Wenjian's work is if we consider the one counter automaton, yes, it's a very weak machine, but still the determinacy of the language accepted, that is just the same as accepted by Turing machine. And also determinacy of probabilistic omega language also similar. Okay. And yeah, this is the last slide, okay? And the relation between modal mu calculus determinacy, we already expressed arithmetical mu and the usual mu somewhat related by black field, and this can be think as this part. This defines the winning region of n difference sigma 02 games, and for this evaluation game of this formula is correspond to this. This has the same complexity as this. Then also we try to extend this to transfinite levels. Yeah, someone did already, but we did also different things. And this is our research direction. Yeah, this is the end. Thank you.
Thank you so much for the nice talk. Any questions, comments?
Yes, time over.
Okay, if no, let's thank the speaker again. Thank you.
Thank you.